Hello, so here we are again for another lovely session of CNG 4412 Steel and Concrete Design. This is going to be part 4 of our 5th lecture in the series, and this is going to finish up our discussion of tension member design. In particular, we are going to look at bolt stagger today, or right now. So this is the third portion of this recorded this evening. The first portion was recorded in class, and here we are. And then the second was recorded shortly before this, and we had that brief couple-minute video introducing the concept of AISC design aids. Okay, so we are rolling and good to go. So the final topic, or well, maybe not the final topic, but the final major topic I want to discuss is bolt stagger. So I alluded to this earlier, and I alluded to this in one of the earlier videos when we discussed net tension area. And bolt stagger is when you have a connection that all of the bolts do not line up in neat little columns. So the method that we have to deal with this is, so in other words, if we go back here, you can see that this is a case where we have bolts that aren't staggered. Everything is perfectly lined up in nice columns, and so you know that a failure plane is pretty much guaranteed to occur along this. Failure is always going to go along the path of least resistance, and if you have something like this where all the holes are lined up nice and equally, you're definitely going to get failure there. However, what if you have something more complex? So our way of dealing with this, it's a rough method, but it's a more of an empirical method. It's a very simple way, but it does work. But for now, to actually label or discuss what bolt stagger is, consider a generic element like this. An element with staggered bolts, an element with staggered bolts, with under load, with two possible failure paths. With two possible failure paths. Okay, so let's say you have an element like this, and I apply a couple lids to this, and first let's look at, let's say that there are holes here, here, and here, like 3 holes. Here, here, and here. And I'm going to apply a tension load T to this. I'm going to apply a tension load T, T, and T. So I want to consider two possible failure paths. Consider two possible failure paths. All right, so on one of these, I'm going to draw the plate twice and illustrate the two different ways that this might fail. So this here, and the same thing, but basically there are two different ways that this could snap into 2 pieces. Here, here, and here. And I'll label the same load, TT, TT. I'll just leave off the T for now, it doesn't really matter. And then let's show the failure planes. So we have a couple possible failure paths. One I might call just a path AB, which would just be like what we've seen previously, directly all the way across, no problem here. A to B. No problem, A to B. The other, though, would be, what if, so that's very easy to calculate. That's, well, relatively easy. It's no more difficult than what we've looked at previously. However, what if we have a different failure plane? Something more like this. And what if the failure plane jogs over between 2 different bolts? This is what we mean when we're talking about a bolt stagger or a failure in a bolt stagger plane. So maybe we could call this, I don't know, DC or CD. Here. So we could have failure path AB or failure path CD. And we have we label this in terms of the code. We have terms S and G, and those are dimensions on this kind of bolt stagger, center to center, where we call S. S is the distance from center to center on bolt in one of the diagonals that goes in the direction of the tensile loading, and G is perpendicular to the tension loading. G. So basically we have a way of see, if you look at this, this is actually a bit tricky. See, this is a pure tension path. Everything along this plane is just being pulled apart. The difficulty thing here is that when we have a diagonal, if we go back here, when we had this kind of system where we had a block shear, we still had very clear planes where this was clearly going to be failing in tension, and this plane was going to be very clearly failing in shear. The problem with this kind of bolt stagger is that we don't, because it's at a diagonal, because our failure path is forced to be at a diagonal or may occur at a diagonal, we don't really have a good way of analyzing that directly in terms of pure shear or pure tension models, because it's a diagonal, so it's going to be under a combination of shear and tension. So how do we deal with this? Well, what we're applying is an empirical method. What we're going to apply is an empirical or an approximate method, and basically it's going to say that when you're calculating your net tension area, your net tension area, you are going to sum up all of the s squareds over 4g's. S square over 4g. Basically, we say that, okay, for this portion of the length, from the length of this portion of CD and this portion of CD, the net tension area is just going to be the simple length, from the edge to the center, etc. And that will be true anytime a line of the failure mode is, and actually, let me, that's fine. And anytime the line of the failure mode is perfectly perpendicular to our tension line, we'll just use the actual length of it. But anytime we have a diagonal, we'll consider the effective length of that diagonal to be s squared over 4g. The reason we have a summation is because if we have more than one diagonal in our failure path, we may need to sum up multiple s squareds over 4g. So here, let's then consider this here. Let's find sort of let's look at how we would calculate each of these, sort of qualitatively a bit. If we had AB, how would we calculate its length? Well, the length net for here would be the width, the actual width of the plate, minus just the diameter of one bolt hole. But that diameter of the bolt is going to be dB plus 1/16 plus 1/16. Or simply the width minus the diameter of the bolt minus 1/8 of an inch. Then, but for CD though, it's going to be a little bit different. The net length is going to be the actual width. The width here to here is the width minus 2 times the diameter of the bolts plus 1/16 plus 1/16. So basically, this is I should probably back up. I may have misled you a bit when I said that this is going to be added as the equivalent length of this. It's more that this is a modification. This is the additional length you get for the diagonal. Is the way you might phrase that. That's the additional length you get for the diagonal. So then we're simply going to add the summation of any s squared over 4g. And if you want to read about this is explained in the same section where net area is described. And this is section, let's see, B4.3b. It's going to be chapter B, B4, 3 lowercase b like this. And it's on page 16.1-20 of this 15th edition of the AISC Steel Manual. 16.1-20, you can see where they describe the s squared over 4g down in the net area calculation. Okay, So again, I do want to emphasize this is an empirical relationship. You can't simply derive it from the length path. If you try to use some geometry and calculate, let's just find the equivalent length of this thing. No, that doesn't work. You can't do that. That's not how this is determined. When I say empirical, I mean this was derived experimentally. Various engineers have experimented with pulling on plates of different lengths with different arrangements of bolt diameters and that sort of thing. And from various experimental analyses, we have found that this is a good rule, good mathematical rule, that basically, again, you just calculate your net area as before, subtracting any bolt holes, but then you just tack on this additional s squared or 4g for each of your diagonals. It's not perfect. It's again from experimental tests and formula development. And this is the reason we can't just directly derive it from base principles, is because it's under both shear and tension. It's a complex situation, and this happens very often in the code. Whenever we have a very, very complex, difficult to analyze situation, oftentimes what the code does is say, okay, this phenomenon is very difficult to directly calculate. Yes, we can use things like finite element models and things like that, but often the code simply says, look, we know we could do a little bit better if we did a very exact analysis, but we're not this is not NASA. We're not doing the super advanced, every last ounce must be shaved off. So instead, what we do is we just say, look, this is an empirical rule. It is not exactly perfect, but it is it's not exactly perfect, and it's slightly incorrect, but it's incorrect in the conservative direction. So if you use this method, this s squared over 4g, you're going to end up figuring out that you're going to end up predicting that you have slightly less capacity than you really will, but that extra is so difficult to predict and calculate. And yes, in very critical applications, you could probably do some sort of finite element modeling of some sort, but for the general code, we're just going to say make a conservative assumption, and this will be fine. Okay. So to illustrate bolt stagger, I want to look at an example here. Okay, so I'm going to look at the same example as the last time, this one here, and I'm going to have the same loads as previously, except what's going to be different is that I've now switched out the bolts. I've changed the bolts up, the bolt pattern up, so instead of having some nice even layout of bolts, I have this kind of bolt stagger. And there are some reasons you might do this. Sometimes there are certain, okay, so the question might be, why would you do this? When you start getting into this, there are certain limitations to how closely you can drill bolts together. If you drill bolts too close together, you end up with Swiss cheese. You end up with a plate that's more Swiss cheese than steel. And so there are certain distance requirements that we're not necessarily going to go into in depth, but there are certain distance requirements that you have to be aware of. And so sometimes you may stagger your bolts just so you can give that extra little bit of distance you need to meet code. Okay, so we're going to repeat this example, but the bottom row was moved to the right a distance of 1.5 inches. Okay, so we're going to have the same loading. So first of all, the same loading, which means our ultimate design load, or our ultimate, not our design capacity, but our design load, yes, is going to be the same. So one, loading. I don't want you to do that in red. Maybe a nice happy green. So our general load cases, our load isn't changing, it's still going to be the same as before. No change. So again, our loading, we said previously, and we calculated on a previous lecture, that the ultimate load for this example was 212. I'll go ahead and use 212 kips. I believe it was 212.2, but I'll just go ahead and use 212 for this example. So we have to prove that this is able to, we'll have to determine whether it is or is not able to withstand 212 kips. Okay, so we're going to go down the long list of possible limit states. So tension member, so I'm first going to look at the tension member, and then I will look at the connecting element. Well, let's see here. So we'll look at the tension member, and then maybe we'll look at the connecting element. Well, actually, yes, I think we'll have time for that. We'll look at the connecting element as well. And so let's look at the tension member limit states. Okay, so first of all, yielding. If you remember from the previous lectures, yielding is going to be based on the gross cross-sectional area. That is just the cross-sectional area without any subtractions for holes, etc. So in this case, for yielding, there's going to be no change. We're still using the same plate, the same gusset plate, the same angle irons, the same L6x6s. The only difference is we're changing where we're cutting the bolt holes. Okay. Next, we want to look at we're going to look at fracture. Fracture. Not block shear rupture, but just regular fracture. So this is going to be based off of the overall area. When again, fracture versus block shear rupture so fracture is going to be where this thing completely tears off. So example, something like this, where it just goes off, tearing down like this. Okay. Fracture here, and let's see, the connection links are going to be a little bit different here. So we have 7 bolt spaces, 1, 2, 3, 4, 5, 6, 7, each at 10.5 inches. So our connection length is going to be a little bit different as well. So here, fracture, remember our equation here, is going to be phi Pn. Phi Pn is equal to phi F ultimate A effective, AE. Where this is our our design capacity is going to be equal to phi times the FU, the ultimate stress times the effective area, and so this is then going to be equal to 0.75 times 58 ksi. 58 ksi. That's the ultimate strength. For our 2 angle irons there, times the area effective. Okay, so this part hasn't changed, the 0.75 and 58. The area effective is what's going to change based off of our bolt pattern here. So what we need to do is we need to compare paths. Let's compare the different failure paths. So I want to look at a 1-hole path and a 2-hole path. A 1-hole path would look something like this. We have basically a couple of possible failure paths. I have a 1-hole failure path that would go like this, and I have a 2-hole failure path that would go like this. So one, it would just be a straight downward path. The other would be a diagonal jog over. Now, we cannot just look at this and say, okay, which one of these is going to control? There may be certain cases where that's obvious. This is definitely not one of them. So what we're going to do is, and you don't need to check every possible one. You just have to check, usually you just have to check an across one and a diagonal one, because it's not going to do something really weird, like it's not going to come down here and then jog over like here and then come down. It's not going to come down here and then try to diagonal all the way across like this. That's not going to make any sense. Overall, it's going to try to take the path of least resistance. And what that means is that, also it couldn't do that because it would have to cross through additional bolt holes. We couldn't tear off just here because these bolts would still be connected. So I suppose we could postulate something like, okay, what if it did something really weird, like came down, then took a right turn, or I guess from its perspective, a left turn, or from our perspective, right turn. It comes down, goes this way, then goes diagonal, then it goes across, then comes down. But that's not going to happen because you're suddenly... everywhere your failure path touches, you're requiring that steel is being torn. And so, generally, the shortest path is going to be the critical one. The only difference is what the trade-off of this one is, yes, this is a slightly longer path, but, so again, what tends to control is the shorter path, but sometimes by going to a longer path, the failure mode gets to go through more than one hole, and holes represent a loss of area. So anyway, that's the base. So we don't need to check every possible one. You really just need to check between if you can get a slightly longer path if you can get an extra hole by going into a slightly longer path, sometimes that will be the critical one. But let's go and calculate each of these, the net area for each of these. Area effective, and we'll be using the area effective, but first we need to calculate the area net. And so let's look at the one hole path. The one hole path. And the area net here is just the area gross, the AG, minus the area of the holes. And plus the summation of s squared over 4g. S squared over 4g times any thickness. There would be a thickness term here as well. However, this is 0 because we have no diagonals in this particular failure path. See on this path here, our straight across path, there are no holes, or there are no, diagonals. So here, this is just going to be very simple. It's going to be 8.76 inches squared minus 7/8. That's the diameter of the bolt. That's not the diameter of the bolts. That's not changing. Plus 1/8 inch for our bolt, our extra hole diameter and our damage calculation or consideration, times the thickness of 3/8 inch. And again, we get the 8.76 square inches by taking the gross area of the cross-sectional area that we find in the code for each angle and multiplying that by 2. And then 3/8 inch times 2 holes. Now at first this seems odd. Why would I multiply by 2 holes? Well, the reason for that is we have 2 angles. So we're going to have to we're basically going to have to multiply anything by 2 for this problem. So here we get a net area of 8.01 square inches. 8.01 inches squared. Then we can also calculate the net area for the 2-hole path. 2-hole path. And here, let's see, our net area net is going to be equal to 8.76. Let's see, 8.76 times here, not 8.76 times, 8.76 minus 7/8 plus 1/8, the same thing here, except now we'll do times 3/8 again. Sorry, except now we'll multiply by 4 holes. And the reason for this here, in this path, we're going to have 2 bolt holes, but each one of those holes pierces 2 plates of steel, or 2 angles, so effectively we have 4 holes. And then plus our s squared over 4g, but our s squared over 4g here, we only have one of them. It's going to be 1.5 times, let me go ahead and just mark this as plus a summation of s squared over 4g, s squared over 4g here. And let's see then. And this then comes to, let me double check something on the calculator here. 1.5 squared plus, or let's see, clear that out. 1.5 squared divided by 1, effectively 10 there. So there's that, and 8.76. So 3/8 times 4, just checking some of my numbers here. So 8.76 minus 1.5 minus 1.5 plus, so let's just see what that's like. 1.26 and plus 0.225. All right, so let's see here. No, that's not, okay, good. Okay, I just had to double check something. And so then this is going to be 8.76 minus, this is going to be 1 times, actually let me just do the calculation here to verify. 1 times 3/8 times 4. This comes to, so minus 1.5 inches, square inches. And this is also needs to be multiplied by the thickness. We do have to multiply by the thickness. This only tells you the length. We also need to multiply by any thickness. And then plus the s squared over 4g, which is 1.5 over 4 times 2.5. Where is that coming from? Over 4 times 2.5. And where is that coming from? Well, 1.5 s. So again, s is the sort of the horizontal direction, or that in the direction of the load, the center to center spacing, and so that's 1.5 inches here. That's your s. Your g is your center to center vertical spacing, or perpendicular to the load, and so that's 2.5. That's where that's coming from. And then we should multiply by the thickness of 3/8 inches, but multiply by 2. So multiply by 6/8 inches. 6/8 inches. So 1.5 divided by 10 times 6 over 8. So then, let's see, 1.5 over 10 times 6 over 8. And so this is then 8.76, basically on my notes here that I normally use, and that something's not, I don't have all my steps shown, so I want to make sure to do this on this one. 7.26 square inches plus 0.1125, or a final area of, so 7.26 plus 0.1125, and I get here a value of 7.37 inches squared. 7.37 inches squared. So let me double check on that. Something's a bit off. 1.5 squared. Let me see if I got that right. 1.5 squared divided by 4 times 2.5. 0.225 here. Let's see. Oh, and then times, that's right. That wasn't coming out quite right. That's 1.5 squared. I knew something wasn't quite right. And then times 6 over 8. So this is a minus, not a plus. Oh wait, no, that should be plus here, and that's plus 0.1. So this minus this is 7.261, and then all of this term together comes out to 0.16875. And if I add 7.26 to that plus the answer there, I do get what I have in my notes, which is 7.43 square inches. In the example I had here that I'm working through, it had a little bit, didn't have enough steps. So I wanted to verify doing some hand calculations or some live calculations here to see if that was going to work. And it did. So our net area is 7.43 square inches. Now, we compare the two. Notice which is smaller. For our one hole path, we have a failure path that is an equivalent failure path of 8.01 inches squared. For the diagonal, the one with the diagonal, the two hole path, it's lower. It's 7.43 inches squared. So again, the failure path tends to look for the path of least length or least effective length. The s squared 4g over 4g isn't an exact length calculation. It's an effective length calculation. And so this one is going to be smaller, so this one will govern. So we will use this as, going forward, we will use this as the failure path, or the net area, or the net area for all of our calculations there. Okay. Let's see. Next, let's move on. Or not move on. Let's just finish calculating tension member fracture. So tension member fracture continued. And And so we know now that we have area net, we need to find our area effective. Area effective is U, the U factor, the shear lag factor, times AN, the net area. And so U, we use that 1 minus x bar over L, and for this case it's going to be 1 minus 1.62 over 10.5. So again, the x bar is the distance from the centroid of one of the angles to the connection plane. So 1.62 in this case, and the length of the connection is going to be 10.5. It's from one end to the other, the first bolt to the last bolt, and that comes to a U equal to 0.85. So then our area effective is going to be 0.85 times 7.43 inches squared, the net area we got previously, or on the previous slide. 7.43 inches squared, and so that comes to a area of 6.32 inches squared. And then we can simply say that phi PN is going to be 0.75 times 58 KSI times 6.32 inches squared. And that comes to a load of 275 kips. So that means that for tension member fracture, oh, it's not 25 kips, sorry, 275 kips. Those are slightly different things. 275 kips. And this is greater than 212 kips, so we are good. So good. So so the tension member is good for fracture. And the tension member is good for fracture. So let's see, what else? What other failure modes do we have? Well, we could have bolt strength, but we're not going to be worried about that one for right now, because that's more later in the semester when we look purely at connections. And in this particular one, though, block shear is actually going to be the same. Block shear is not going to vary substantially, because here we calculated block shear based off of a failure line kind of like this before. The number of bolts really isn't going to change. The number of bolts in there, it's not going to really change, so we don't need to really be worried about that. So for this particular example, block shear and bolt strength are the same as the previous ones, so we don't need to revisit those. And bolt strength the same, although block shear is the same, but bolt strength is just something we aren't looking at we are not looking at yet. So block shear same as before. Block shear is the same as before, but here then, let's see. So again, if I can come up with a better explanation for why it's the same, well, let's see. You're still going to be using the same length, basically the same, because, okay, why is that going to be the same? Let's think about that. Let's go back to this calculation here. Well, it's based off of when we do the tension plane, we're doing this based off of a net, we're doing this based off of a net tension, right? And so it's going to be in tension here, and it's just not going to generally change that much. I wish I could come up with a better explanation for that. Let's think about that. Even if it goes like this, we don't get to take into account that extra diagonal, so we just consider its length to be about the same. Because that f squared over, or that s squared over 4g, that's purely for your fracture state. So we can't use that diagonal here. So we would end up calculating a length. We would still subtract this bolt here, but we would just end up subtracting 2 bolt holes, considering a length like this, and it's not going to change the. We can't take into account the extra, little bit extra capacity we get for the diagonal, because the s squared over 4g rule that does help you out, but it's only for the case of fracture. So block shear is the same as before, and bolt strength is not considered at this time. Not considered at this time. So next we'll move on to looking at the connecting element. So connecting element. Let's look at the connecting element limit states with staggers. With staggers here. Now this particular one, we don't need to worry about block shear because, again, you can sometimes have block shear with the gusset plate, but this particular one, it is so much larger dimensionally than our angle irons here, and it's so much, it's actually made of stronger material. So there is no conceivable way that this thing is going to fail in block shear before our angles do. Anyway. Let's just go down the list though. But if you really want to be thorough, you could check it. So yield. Well, again, this is going to be no change versus the case with no bolt stagger, because yield is based off of your gross, not a net area. All the bolt stagger does is change how you calculate your net area. Okay, so fracture. Then let's look at fracture. And we'll have the same kind of two-hole path and one-hole path. And so in fracture, your equation is going to be that phi Pn, although they tend to use phi Rn for your connecting elements, so maybe I could write phi Rn is equal to phi Fu Ag, or sorry, A net, ultimate strength times A net. Now for the one-hole case, we have no stagger. So we could look at, backing up to this, I could have this kind of thing, and this is not going to control. We have no stagger. We found that path is actually not the critical one, and if it's the and so it's not going to be the critical one likely for the other one as well. So no stagger, will not control, at least for this particular problem. If you find that the one-hole path is going to be, so basically we only really need to check once. If we find that the two-hole path is critical for this element, the tension member is probably going to be, almost certainly also be critical for our connecting element. So will not control. Then the two-hole case, if you include the stagger and you work through that, if you do include the stagger, and you work through all the equations, you will get that and I will challenge you to come up with this number yourself, you will get that the net area, AN, is equal to 5.225 inches squared. So your challenge is to try to figure where that number came from. Again, I'll tell you where it came from, but I'll give you a challenge to verify that. So to do that, you would take this length here, you take the entire length of the failure path, the vertical here, the gross area. So this entire area of the plate, subtract two bolt diameters from it, and then add the 1s squared over 4g, just this diagonal here, for just that diagonal there. So our net area is going to be 5.225 inches squared. And then we do have something that we don't have to worry about for just regular tension members. And that is that we do want to check the design limitation or the geometry limitation to check that AN is less than or equal to 0.85 times the gross area, AG. 0.85 AG here, 0.85 gross area. So that means that here, 5.225, we need to make sure that our net area, 5.225, is less than or equal to 0.85 times the gross area, which is 6 square inches. And this reduces to 5.225 is less than or equal to 5.1 inches. So this is actually a case where this is no good. We could not really use this kind of gusset plate design for our for a case with bolt stagger. So we would need to redesign. Although not necessarily redesign. This is not really a redesign case. Sorry, what this means is basically our net area is limited to this becomes an upper limit. No good. Use 0.85 AG as our net area as AN. So for connecting elements as AN, again for connecting elements, we want to use, we calculate the net area however we would, but we have an upper limit. We have to make sure that our upper limit, or sorry, we have to make sure that our net area, however we calculate that on our connecting element, never exceeds is 0.85 or 85% the gross area. So we're never allowed to use more than 85% of the gross area of the connecting element when designing for tension or when calculating tension. So we're going to use 0.85 AG, or again 0.85 AG would be 5.1 inches squared. That's what the code allows us to use. And so then phi RN is going to be 0.75 times 80 KSI, the ultimate strength of this connecting element, of the material, the ultimate strength of it, ultimate stress of it, times 5.10 inches squared. And this is then 306 kips, which is greater than 212 kips, our ultimate load, so we are good. And that finishes up this example. May it never return. Okay, so we are good. We have proven this is good. The connecting element is good in both yielding and fracture, even in the case of bolt stagger. Well, actually, bolt stagger will tend to help you, but anyway. Okay, in both yielding and fracture. So that's another reason you might actually want to have a bolt stagger. I said previously there are sometimes dimensionality requirements, like you have to have bolt distances a certain amount away, you have to have bolts a certain distance away from each other, etc. But bolt stagger does tend to give you a slightly higher length of failure plane in certain cases. So that might be a case where it would actually control. So you might there might be times where you deliberately actually induce a bolt stagger for the purposes of having a longer failure plane and thus a slightly higher failure capacity. So here, that's not going to be enough to, now if you have a system or a steel member or a frame or something like that that is just grossly failing, that is failing by massive amounts, switching to staggered bolts is not going to save you. If you are off by 30% or something, and if your member needs to carry 900 kips and you only have a capacity for 700 kips, well, staggering the bolts isn't going to make much of a difference. However, if you have something that's almost across the line, if you have maybe something that's 900 kips and that needs to carry 900 kips, and according to your current code check, it can only carry, if it has to carry 900 and your design capacity is only 895, well, maybe going to that bolt stagger, if the failure mode that you're dealing with is a fracture failure mode, not if it's yielding, that's not going to help you. But if you have a fracture failure mode controlling, well, that might actually be a case where that's important. That would make a difference. Okay. So I have one other sort of limit state that I want to talk about for tension members. Now, this isn't really a true limit state. This doesn't actually have anything to do with strength. This is more a constructability limit state, and we call this the slenderness check. Tension member slenderness check. The tension member slenderness check. So this is in section D, and This is on right at the beginning of chapter D. It's section D1, and it's on 16.1-28. So so again, this is section chapter D. Let me do this in black because I like to save. I'll do all of my titles in blue. So this is chapter D, section D1. Section D1, page 16.1-28. So, there is no maximum limit for the slenderness of tension members. No maximum limit for the slenderness of tension members. So you can make them as slender as you want. This is not actually a code requirement, so I got to be careful with my language. This is more of a recommendation for good, sort of what the AISC thinks is good practice. So everything else is actually, legally mandated. If you're designing steel, you have to. If you're designing a steel structure in the U.S., you generally are going to have to follow this code, at least for most major structures of tension members. But it does provide a recommendation. AISC recommends. Okay, so think about this. Consider a long, slender element. Well, actually, let me just provide the rule first. L over R is less than 300. Where L is your length and R is your radius of gyration, and that would be the most critical radius of gyration. So in this case, it would be the smallest, or that'd be the largest, I suppose. That would be again, we want to make sure this is less than 300. So the more critical one would be where this is smaller. So the smaller R controls. Smaller R controls. And you of course find your R, your radius of gyration, with your other section properties in chapter 1. So L over R is less than 300. So where does this come from? Well, let's think about this. So if you have a member, imagine a very long, slender member. If I try to push this in compression, imagine taking a light, any kind of very light, slender thing, almost like a blade of grass or a piece of paper or a toothpick or something very weak but still long and slender, and you apply a compression load to it. Well, what does it do? Well, it tends to buckle, and we'll talk about buckling load in a couple weeks when we get to compression members. So we can have buckling here, so popping out and failing like buckling. So in buckling, or in Euler buckling, for example, you get failure long before you have the actual ultimate load or the elastic limit or etc. But with tension members, that doesn't apply. You can't cause a tension member to fail by buckling. The only way to get a tension member to fail is by making it yield, or by making it a fracture, or by block shear or something like that. So here, if you apply a tension members, of course, cannot fail in buckling. Tension members cannot fail in buckling. So then, the question is, how slender can you make them? Well, the AISC manual does not provide any code that says, okay, for strength reasons, if you make your tension member too slender, it's going to snap in half, it's going to break, it's going to buckle. This is not that kind of limitation. This is more a practicality or constructability type of thing. So the longer and longer and longer things get relative to their width and relative to their cross-sectional area, relative to their moment of inertia, etc., the more flexible they get. So, for example, imagine for a moment that I took a really big steel section, maybe not a massive one, but maybe like a W8 or something like that. A decently strong steel section, the type that there is no way I would ever be able to bend by hand, or a W12 even, or something. And I support this thing on basically a set of really, really good roller bearings. So imagine I could put this on a frictionless surface but then fix it on one end. So imagine I could have this beam that was really, really long, and I can't draw a top flange. Save my life. Here. So I have the bottom flange here. And so I effectively put it on a series of roller bearings. And how you would actually do this in real life. I suppose you could actually have a bunch of roller bearings. There'd have to be a set of, very finely ground ball bearings, etc. And imagine that I could just slide this back and forth. So imagine, looking at this from above. So this is looking at it from the side there, at this, and then looking at it from above, I would almost have like this. I'd see a long, long beam. And let's say this is thousands of feet long. I make a beam for some reason, even a W8 or something. A W8 would be a good example. It's not going to collapse because I have roller support. Maybe, let's say I have a bunch of them, roller supports every 2 feet or something like that. A real crazy device. You would build this only for the sake of proving that this is possible. And so this thing is supported vertically, so it's not going to bend down and droop down. But it effectively has no resistance to lateral movement. The only resistance that could occur to moving this thing from side to side would be from this thing's own internal resistance. Now, if I give you a chunk of a W8 that's 5 feet long, 3 feet long, even 10 feet long, etc., there is no way that you're going to be able to bend that by hand. Steel's pretty strong stuff. There is no way that you're going to be able to bend that with your bare hands. However, if I went and I'm not the strongest person in the world, but if you gave me if you built me a thing like this, so I didn't have to worry about holding the thing up, and I didn't have to worry about friction on the bottom. So of course it was just dragging in the dirt. Well, then the frictional force on the ground would cause that not to work. But if this thing effectively had zero rolling resistance, I could just come along here and grab it and just wobble this thing back and forth like at will. I could almost just I could just bend this steel beam, this giant 8-inch W8, this giant 8-inch, well, relatively giant, at least for hand proportions, hand strength anyway, this 8-inch tall steel beam, and I could just bend this thing back and forth with my bare hands. And that's of course impossible to do if you have something that's any normal length of feet long, like 3, 4, 5, even 10 feet long. But if I make this thing ridiculous, if I make this thing, I don't know, like a mile long, that would be an incredibly expensive setup just to prove a scientific point. But don't do that. That would cost a lot of money. But anyway, let's say it's a mile long. So it's just this mile long W8. That's going to be expensive. Just the shipping alone. My God. And find a place to set up. Wow. Okay, but anyway, and why is that? Well, the flexibility of something, as you learn from mechanics of materials, bending or displacement is going to depend not only on the moment of inertia, but the length. And it tends to increase with the third or the fourth power of length, that kind of thing. So if you have this set up with a really incredibly long length, well, if you take that length and multiply it to the third or fourth power, oh boy, that's going to be pretty crazy. And so I think that should be a third power, I believe, with a point load. Anyway, so this thing's just going to wobble back and forth. And the reason for that, yes, it's a steel beam, but you've taken that steel beam and made a piece of spaghetti look positively stout. You basically have said you have turned that steel beam, even though it's 8 inches thick, is going to have the same cross-sectional ratio, the same length to width ratio as like a tiny, 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 very fine wire or something like that. So you can have something, if an ant tries to bend a wire, it's not going to be able to do that. But if you can hold a wire an infant can hold a small wire and bend that fairly easily. It's all based on the bending arm, the moment arm. But anyway, so we see, and this is really what this is coming down to. I know this is a long-winded way of getting there, but we want to limit our because this is tension member. We are designing tension members still, so we don't have to worry about a bending moment. However, anytime your members start to get too long, they start behaving like spaghetti. So in the sense that what happens if you have a very long, thin member and you try to lift that thing up? If you have a very, very long skinny member and you need to lift this thing on a crane to pull it up, well, this thing, if it's too long and thin, it can't even, in other words, it's so long and thin, it can't even support its own weight without just collapsing. This thing might just bend massively under its own weight as you lift it. And also, if it gets too thin, it can start being subject to damage as you're moving it around, deploying it, etc. So basically, oh, that's not right. I don't want a highlighter. Pen. So again, this is based mainly. I can make it. I want to do this in black. We have it not a code requirement, but a recommendation of L over R is less than 300. And again, this is not a requirement, but a recommendation, and it is based mainly on economics. Handling, potential damage during transport, construction, etc. Steel tends to be pretty durable, at least in terms of most building materials, so people don't tend to baby steel as they're moving it around. You know, you think of a steel, even the term steel or steel beam, or, you know, if I say to somebody, you know, if I go up to somebody and say, man, that was like getting hit by a steel beam, even somebody who has no idea how to calculate steel, design calculations will have a visual image of what that means. When we say steel in, you know, casual parlance, we have an image of something that is fairly durable, and in reality, most steel sections are. They can even you can abuse them a bit during transport, and they're probably going to be just fine. However, if you start making these things really, really skinny relative to their length, you start running into problems. You start having things that are more easily damaged. Also, you start having things that well, even if the math in your things that in your design says that you can get away with a 200-foot long member, how are you going to get that to your construction site? Now, yes, maybe theoretically you could order multiple of them, smaller lengths, and weld them together on the site with some full pen welds or something. But if you try to move that out there in one piece, how in the world are you going to move something 200 feet long? That's going to be crazy. So that's going to be a problem. Anyway, the point being, the longer members get relative, both just raw length, and more importantly, longer relative to their radius of gyration, to their stoutness, basically, you end up running into problems with damage, transport, contraction, etc. When we get into compression members, we will actually start calculating limitations on L over R ratios, etc. But for tension members, we just say, okay, this is not a actual strength requirement, but it is just sort of a good design practice. Okay, so next I want to do a summary of the analysis procedure, and then talk a bit about maybe design of tension members. Okay, so summary of tension analysis. Everything we looked up to previously has been tension analysis. So summary of tension analysis. Summary of tension analysis. Okay. So we have both our tension member and our connecting element. And let's see. And what limit states do we need to consider? Well, first of all, for our tension member, in our general form here, is going to be that phi PN. Phi PN is greater than or equal to P ultimate. Our resistance factor times our nominal capacity is greater than our ultimate factored load. Then for our connecting element, our general equation is phi Rn is greater than or equal to P ultimate as well. Okay. Then here, let's see. So, and we can, and again, we see tension member design is in general chapter D. Then with some notes there, here and there. And then our connecting elements are found in chapter J. Okay, so here, let's see. Then let's summarize the individual failure modes that we've considered in this and previous lectures. Yielding, fracture, block shear, and block shear, essentially. And the same here, yielding, fracture, and block shear. If you know how to do all of these, then you'll be up to date in terms of our tension member analysis lectures. Okay, and then we do add one other thing, and that is our slenderness. I'm putting this in green because it's not really a strength limitation, just sort of a best practice. And so the only other question is, what is still missing? What is missing? Well, we haven't considered the actual connection of our tension member and connecting elements. We've considered connecting elements, but not things like bolts and welds. We're going to be saving those towards the end of the semester. Bolts and welds. So for now, whenever we design something with a bolt and weld, we are going to simply assume it to be adequate. All right, I do have some notes on the analysis of, or the design of tension members, but I think I might actually modify the schedule a bit and continue on with one final lecture on tension members on Thursday, where I'll do some long-form design examples of tension members. Okay, and so I think I'll save that for Thursday. I think that will do it here for lecture 5. If you have any questions, feel free to contact me, see me in class, email me, see me during office hours, etc. That'll do it. That concludes the design of tension, or the analysis of tension members. We've looked at how they can fail, yielding, fracture, block shears, and also for both a tension member and connecting elements. We've looked at staggered bolts. We've looked at slenderness, and we're still haven't gotten to bolts and welds and design yet. Whew, welcome to steel design. Okay, so that'll do it. And as always, thank you.